When we think of dark matter, we think of something ghost-like, something hidden from us, something that we can't see, something that we can't interact with. But the truth is, the evidence for dark matter is there, but we have to look in the right places. Dark matter is all around us. The sun, every second, it emits trillions of neutrinos, a form of dark matter that we cannot see and we rarely interact with. The average neutrino can travel through a light year of lead before it interacts with the nuclei of an atom. Its cross-section, or probability for interacting with a particle, is so tiny because it does not emit nor does it receive light. It does not interact with the electromagnetic field. It is completely and utterly devoid of an electromagnetic interaction. And yet, deep underground, they've been detected at many locations, including Fermilab. A new experiment, in fact, will detect them at greater numbers than ever before. Currently under construction, and with a detector at both Fermilab and a FAR detector at the Sanford Underground Research Facility, also known as SURF, which is located in South Dakota. They will observe neutrinos produced at Fermilab. An intense beam of trillions of neutrinos from the production facility there will be sent over a distance of 1,300 kilometers with the goal of understanding the role of dark matter neutrinos in the universe. More than 1,000 collaborators are working on this project, and the experiment is designed for a 20-year period of data collection. They will investigate the strange occurrence of neutrino oscillations, a process known to occur with solar neutrinos produced in the sun, where the neutrinos can oscillate and change flavor. You see, there's three types of neutrinos: electrons, muons, and tauon neutrinos associated with their respective lepton particles. The electrons are the lowest mass and more stable form of the lepton, whereas the muons and tauons are higher mass, shorter lived, and higher generation of particles than the electrons. Electrons do not oscillate and change flavor into tauons or muons. Electrons stay electrons. Electrons can change into different energy levels, of course. However, they never change their identity. The fact that neutrinos do oscillate and change flavor, thus becoming a different type of particle, and that this oscillation is periodic and occurs as a quantum interference effect, where we have the three pure flavor states of electron, muon, and tauon neutrinos all combined into one superposition, and the interference between the different states produces the probability of detecting one of the three types. The fact that the neutrinos behave this way is a huge shock and was not predicted by the standard model of particle physics. Thus, we already have evidence confirming that the standard model is not enough to describe nature. The proof of neutrino oscillation was found in the early 2000s, yet we still do not understand how it works, even if we have the mathematical formulation that explains it. We don't understand exactly how to make the standard model better so that it incorporates neutrino oscillation and neutrino masses into the picture, because originally it was thought that neutrinos were massless. The standard model of particle physics also predicts them to be massless, but this is not the case. Thus, hot dark matter, also known as neutrinos, is our first major scientific problem that we need in order to fix the standard model and make a working model of nature and particle physics that incorporates everything and can explain everything. Therefore, this observational experiment is extremely important and will play a big role in the future of science. But what about cold dark matter? The dark matter out there in space that's supposedly helping form galaxies. What observational evidence do we have that it exists? The image you're looking at right here is from the Hubble Space Telescope, and it shows the distribution of dark matter, as in cold dark matter, in the center of a giant galaxy cluster named Abell 1689. This contains about 1,000 galaxies and trillions of stars. Hubble can't see the dark matter directly, but the astronomers have inferred its location by analyzing the effect of gravitational lensing, where light from galaxies behind Abell 1689 is distorted by the intervening dark matter within the cluster. The researchers have used the observed positions of 135 lensed images of 42 background galaxies to calculate the location and amount of dark matter in the cluster. They then superimposed a map of these inferred dark matter concentrations, tinted them blue on an image of the cluster taken by Hubble's advanced camera for surveys. If the cluster's gravity came only from the visible galaxies, the lensing distortions would be much weaker than they are. Thus, this map reveals that the densest concentration of dark matter is in the cluster's core. Abell 1689 resides 2.2 billion light years from Earth. This image was taken in June 2002 by the Hubble Space Telescope. In another piece of observational evidence that dark matter exists, we see a composite image showing the distribution of dark matter, galaxies, and hot gas in the core of a different merging galaxy cluster called Abell 520, which formed from a violent collision of massive galaxy clusters. The natural color image of the galaxies was taken with NASA's Hubble Space Telescope and with the Canada-France-Hawaii Telescope in Hawaii. Superimposed on the image are false colored maps showing the concentration of starlight, hot gas, and dark matter in the cluster. Starlight from galaxies derived from the observations by the Canada-France-Hawaii Telescope is colored orange. The green-tinted regions show hot gas as detected by NASA's Chandra X-ray Observatory. The gas is evidence that a collision took place. The blue-colored areas pinpoint the location of most of the mass in the cluster, which is dominated by dark matter. Dark matter is an invisible substance, yet we can see its gravitational influence here in this incredible image. Just because we haven't seen it directly with the telescope doesn't mean that we aren't looking for it directly. In fact, the Alpha Magnetic Spectrometer is a particle physics experiment module that is mounted on the International Space Station. It's recognized as a CERN experiment, and it's a detector that measures antimatter in cosmic rays. Cosmic rays are high-energy protons and atomic nuclei that move through space at nearly the speed of light. They originate from the sun and from outside of the solar system in our own galaxy and from distant galaxies. This information is needed to understand the formation of the universe and search for evidence of dark matter. The principal investigator of this experiment is particle physicist Samuel Ting, and the launch of the Space Shuttle Endeavour carrying this experiment took place on May 16, 2011, and the spectrometer was installed May 19, 2011. It's recorded over 60 billion cosmic ray events and 90 billion after 5 years of operation. Incredibly, it's observed over 400,000 positrons, which is a form of antimatter, essentially the antimatter version of the electron. Because cosmic rays are so energetic, it was thought that they could potentially interact in such a way that a dark matter particle, which is thought to be very high mass, could potentially be produced and detected by the detector. As of this moment, no dark matter particle has been detected. Thus, our understanding of dark matter is showing that it's still in its infancy.